So power distribution is a very common application of transformers. If you walk around outside up on many power poles, you'll see this. You'll see these large gray cylinder things. Sometimes they have these little things coming out of them like that. They're called pole pigs. And this is the idea behind it. You've got a generator voltage. And it has a really long wire. And it goes to your load. And although the resistance is up really on both sides, I'm just going to draw the resistance on one side to make it simple. If it's a really big, thick wire, it might be very small resistance. Maybe it's just 1 ohm. Your V generator, maybe it's, it's 110 volts, 120 volts. Let's, to make the numbers easy, say it's 100 volts RMS. And we've got our load over here. And, let's say this load is using a whole lot of current. Let's say it's like 100 kiloamps, which again is pretty reasonable for a load the size of Nichols Engineering Building. What's your load power? What power is being delivered to the load? If we ignore the line losses, we've got 100 volts RMS, and we've got 100 kiloamps, and so we've got 10,000 kilowatts, which is 10 megawatts. So that's pretty good. Make sense so far? And we just have to, it's probably worthwhile also finding out what the line loss in our wires is. So that's equal to the power of your 1 ohm, which is equal to the to your current flowing in here times the voltage across the 1 ohm. Let's see. So that's going to be equal to the voltage across the 1 ohm is equal to the current through it times your 1 ohm resistance. In fact, I'm going to keep just using numbers for a second, times your Z of your line. So that's equal to your I squared times your Z of your line. So what we've just said is it's equal to, how much current do we have? 100 kilos squared times 1. So 100 kilos squared, that's going to be 10,000. And a kilo times a kilo is a mega. And so that means we've got 10 gigawatts. So do you see the problem? We're delivering 10 megawatts to our load, and we've lost 10 gigawatts in our line. So our efficiency is terrible. Our efficiency, which is power out over power lost approximately, is 10 mega over 10 giga. So we're at 0.1% efficiency. For every 1,000 watts we're developing in our generator, we're actually only delivering 1 watt to our source. Everything else is being lost in our load. So I can't imagine a worse thing than this. What's the solution? What do you think, Dom?
So I want to go back to the class. Like power factor correction, adding a.
So what's the power factor here as I've drawn it? I haven't actually told, for everything else, I'm handling this as purely resistive. So there's nothing to correct.
So then I'm not sure.
Well, what are we talking about?
So I was thinking power factor,
remember,
I might be confusing that with.
So we're talking about real power everywhere here. So we just don't have a power factor. A power factor is 1.
I was confusing that with the efficiency.
Yeah. I understand what you're saying. Yeah, these aren't degrees; these are percents. So, and don't even really worry about the efficiency as much. I just want you to see power out, power lost, and then realize no one's going to make a buck on this. So the solution is we take that generator, which is 100 volts RMS, and we're going to put it into a transformer. And it's going to be a transformer that really boosts up that voltage up a lot. It's going to have an N of 1,000. We haven't changed our line. All we've done is we've added two transformers, one at the start and one at the end. The one at the start boosts the voltage up. The one at the end drops the voltage back down. Now, this should still be, the power should still be 100 volts. The current going through it should still be 100 kiloamps. We haven't changed anything, right? If we've boosted it up by 1,000 and dropped it by 1,000, it should be the same. And so we're still looking at the same 10 megawatts at our output. So as far as our customer is concerned, they don't even know we've put in two transformers. It hasn't changed their life at all. But what happens to our line loss? Our line loss is still going to be I squared Z, no change there. But what's our new I? We had, if we've got 100 kiloamps here, same thing as saying 100 kiloamps here, our voltage here goes up by a factor of 1,000. Now instead of being 100, it's 100 kilovolts. Really high voltage power lines. But what's happened to our current? What's it gone down to?
Current has gone down to 100 over 1,000.
It's gone down by 1,000. So that's 100 kilo divided by 1,000, which is?
I don't know.
100 kilo over 1,000?
Kilo.
A kilo is 1,000. So 100 kilo over 1,000.
One.
Just one. So it's just 100 amps. Now our line loss is equal to that 100 amps squared times our 1 ohm, which is 10 kilowatts. Now compare our output power delivered to our power lost.
Right. So now we have more.
Now our efficiency is close to 99. Now our efficiency is, to get this exactly right, I should have said power out to power in. Power out is 10 megawatts. Power in would be that 10 megawatts plus that 10 kilowatts. So that would be that. And now we're looking at, 99.9% efficiency. Nearly all of the power that we're generating is being delivered. And so this second example is exactly why we see these high voltage power lines everywhere. We want to have these incredibly high voltage power lines because then we have these relatively low current lines, and then the resistive line losses just pretty much go away.
So where does that 0.01 come from at the end of the 10? That P out over P in?
So the input here has got to be the whole total power. So it's the power that's been lost in the lines, which we said is 10 kilowatts, plus the power that's being delivered, which is 10 megawatts. Maybe it's clear if I said it this way. P out, which is going to be P load That's our power output over P line loss plus P load. So that's going to be 10 megas over 10 megas plus 10 gigas, which is 10 megas over 10.01 gigas, which is pretty close to exactly 0.1%. This is equal to power load divided by power of the line. Wow, that's hard to read. Power of the line plus power of the load. So that's going to be 10 megas over 10 megas plus 10 gigas. So that's going to be 10, I'm sorry, it's no longer 10 gigas that we're losing. We're now losing almost nothing. We're losing only 10 kilos. So that's going to be 10 megas over 10.01 megas. And so that's going to be
Okay. Yeah.
99.9%. About.
All right.
Yep, that's it. So that's why, that's the other big, so the two big uses of transformers are, number one, for impedance matching. If you play guitars, you'll see in amplifier boxes, guitars have a relatively high output impedance. They can't change it. It's just in their pickups. They have a high output impedance. So you'll usually see a big impedance matching transformer to couple that high impedance signal as well as possible. In a lot of big speaker drivers, you'll see the same thing. You'll see if you've got an old tube amplifier source that has a really high output Thevenin impedance, and so you'll see a big heavy transformer that couples the two. The other big use of them is in power distribution, so that your relatively low voltage generator, which might only be 100 volts, somehow gets pushed up to 100 kilovolts, so that its current drops all the way down, so that its line losses drop all the way down, even at the expense of having big transformers at the generating station, and then all these transformers at your load. Good deal.
Sure.
That's it. That's everything you need to know about ideal transformers. And now the only other question that I could ask about this is, how do you, what could I ask? I could now ask a more complicated question about the input, and then you would know if you see a transformer, first thing you do is you just take the Thevenin equivalent of that transformer and push it back on your input stage, and now you're just back with a standard problem that you've seen before this lecture without the transformer. You use this Thevenin equivalent to get rid of your transformer, and now it looks like just something you already know how to work with.